Welcome back to our deep dive series. Today, we're digging into some really fascinating recent machine learning research.
That's right. We're looking at a paper that just came out in March, Implicit Bias-Like Patterns in Reasoning Models by Li and Lai.
And it tackles this idea of bias in AI, but from a slightly different angle than maybe what we're used to.
Exactly. Much of the focus, has been on the outputs. Does the AI say biased things? And models have gotten better at avoiding overtly stereotypical outputs, partly thanks to things like RLHF.
Right, the alignment work.
Yeah, but this paper asks, well, what's happening before the final answer in the reasoning process itself? Could there be bias lurking in how the model actually processes information?
Which is a super interesting question. And they use a pretty clever method to investigate it, borrowed from psychology.
They do. They adapt the Implicit Association Test, the IAT. Many people might have heard of it or even taken one online.
That's the test that measures reaction times, right? To see how quickly we associate certain concepts.
Precisely. Like pairing social groups, say men and women, with attributes like career or family, or racial groups with positive or negative words.
And the idea is that if you're faster at pairing concepts that align with common societal associations, even unconsciously,
it suggests a stronger implicit or automatic association. Slower responses for pairings that go against the grain, like maybe men with family for some people, can indicate that underlying bias. It taps into cognitive efficiency.
Okay, so that makes sense for humans in reaction times.
Yeah.
But how do you measure reaction time or cognitive efficiency in a language model? They don't have fingers on keyboards.
Right. No fingers. But what these advanced reasoning models do have is intermediate processing steps. They generate reasoning tokens to work through complex problems. Think of models like OpenAI's O3 Mini or DeepSeek's R1.
So those step-by-step chains of thought we sometimes see.
Exactly. And those reasoning tokens, the authors argue, give us a window into the model's processing effort. It's the analogy to human response time.
So the core idea, the hypothesis, is that if a model has learned associations from its data,
it might take more computational effort, more of these reasoning tokens, to process information that contradicts those associations, just like it takes us longer in an IAT for incompatible pairs.
Got it. So they built an IAT specifically for reasoning models, the RMIAT.
Yes, the reasoning model Implicit Association Test.
How did that work in practice? What did they feed the model?
They created lists of words, social categories like men, women, European Americans, African Americans, young, old people, and attribute categories like career, family, pleasant, unpleasant, science certs.
Okay. Standard IAT-like categories?
Right. And then they prompted the model, specifically O3 Mini in this study, to categorize words. Crucially, they set up two conditions.
Let me guess. Compatible and incompatible.
You got it. Association compatible, where the task aligned with typical stereotypes, like pairing men with science concepts, and association incompatible, where it went against the stereotype, like men with arts concepts.
And they had to structure the prompts carefully.
Very carefully. Since API calls are stateless, the model forgets the last interaction. Each prompt had to contain all the instructions. And to avoid results just being down to weird freezing, they used 20 different prompt variations for each task.
That sounds thorough.
It was. They ended up making almost 13,000 API calls, measuring the number of reasoning tokens used for each categorization task in both compatible and incompatible conditions.
Okay, the moment of truth. What did they find? Did the models hesitate or use more tokens for the incompatible tasks?
They absolutely did. In 9 out of the 10 different RMIATs they constructed, the model used significantly more reasoning tokens when the pairing was association incompatible.
9 out of 10, wow. Were some effects stronger than others?
Yes. The biggest difference is large effect sizes, statistically speaking, were in tests like instruments, weapons versus pleasant, unpleasant, men, women versus science, arts, and flowers, insects versus pleasant, unpleasant.
Interesting. So not just social biases, but other strong associations too, like flowers being pleasant.
Right. But they also found significant medium-sized effects for pairings like European African Americans with pleasant, unpleasant, young, old with pleasant, unpleasant, and men, women with career, family, or maths arts.
And which one didn't show an effect?
The only one with no significant difference was mental physical diseases paired with temporary permanent. Notably, that's the one test that didn't involve social group stereotypes.
That contrast is telling in itself.
It really is. On average, across the board, the model needed about 53% more reasoning tokens for the incompatible tasks. That's a substantial computational cost for going against the grain.
It really paints a picture of the model having to work harder computationally when faced with counter-stereotypical information.
Exactly. And there's another piece that adds to this picture, model refusals.
Oh, right. Where the model just refuses to answer.
Yes. And interestingly, these refusals only occurred in the 3 tests related to race.
Only race-related.
And get this. 85% of those refusals happened in the incompatible condition, when the model was asked to make a counter-stereotypical association involving race and pleasantness.
So it was more likely to refuse the counter-stereotypical task than the stereotypical one.
That's what the data shows, which is quite revealing. You might think alignment techniques like RLHF would make it refuse stereotypical pairings, but they saw the opposite.
And did those refusals correlate with token count?
They did. Refusals generally had very high token counts leading up to the refusal point. When the authors included these refusals in their analysis, just counting the tokens used before it stopped, the estimated effect size for racial bias actually got even stronger.
Wow. That suggests the alignment might be overlaying something, but the underlying difficulty with counter-stereotypical ideas is still there, and maybe even quite deep.
That seems to be a key implication, yeah. It suggests these bias-like patterns might be embedded pretty deeply, potentially resisting current alignment methods that focus more on output filtering.
So let's zoom out. What are the big takeaways here? Why is this important for people working on or deploying these models?
Well, the first big one is that reasoning models show these processing patterns that really do look analogous to human implicit bias. It's not just about the final word, it's about the journey to get there.
And that internal processing difference could have real-world impacts, even if the final output seems okay.
Absolutely. In complex decision-making, these subtle processing differences could, perhaps, lead to skewed outcomes over time. Plus, there's a practical side. Needing over 50% more tokens for certain tasks has a real computational cost, and potentially an environmental one at scale.
And the refusal finding is also worrying.
Definitely. If models are more likely to balk at counter-stereotypical information, they could inadvertently end up reinforcing existing societal stereotypes simply by finding it harder, or even refusing to engage with challenging ideas.
Of course, no study is perfect. The authors mentioned limitations, didn't they?
They did, which is good scientific practice. Firstly, this was just one model, O3 many. We need to see if this holds true for other reasoning models, different architectures, different training data.
Makes sense. What else?
The way they got token counts from the API wasn't super precise. It came in chunks of 64 tokens. More granular data or direct access to the model's internals would be ideal for future work.
Right. Better measurement tools.
And finally, apart from the refusals, they didn't deeply explore how this extra processing effort impacts the actual performance or accuracy on downstream tasks. Does working harder on incompatible tasks make the model subtly worse at them in other ways? That's still an open question.
Okay, that gives us a great picture of the paper itself. Shall we move on to our novel notions segment, thinking about where this could lead next?
Let's do it. This paper definitely sparks some ideas.
So novel notion number 1.
Okay, how about this? Investigating the cognitive load of debiasing techniques.
Ooh, okay. So if processing counter-stereotypes takes more effort,
then what happens when we layer active debiasing strategies on top of that, like prompting the model during reasoning to check its biases or consider alternatives?
Well, the obvious part is that adding steps will add tokens, right? More processing means more tokens.
True, that's the straightforward bit. But the less obvious, maybe more interesting part, is where those extra tokens get used. If we can pinpoint which debiasing steps cause the biggest token spikes,
you could see which techniques are the most computationally expensive.
Exactly. It could help us develop debiasing methods that are not just effective, but also efficient, balancing bias mitigation with computational resources, which is increasingly important for sustainable AI.
I like that. Merging bias research with efficiency research. Okay, what's notion number 2?
This one's a bit more speculative, exploring latent association drift over long reasoning chains.
Latent association drift. No, okay, unpack that.
So we know incompatible tasks take more effort. Could it be that over a really long, complex reasoning process, this extra effort makes the model more likely to sort of drift back towards its easier, learned, compatible associations?
Like a cognitive fatigue in humans, where sticking to the harder, controlled thought process gets tiring.
Kind of, yeah. That's the analogy. The obvious thought is just that more processing gives more chances for errors or reversion.
But the non-obvious angle?
The non-obvious angle would be looking for subtle shifts within the reasoning tokens over a long chain. Even if the final answer is technically correct according to the incompatible prompt, do the intermediate steps show a gradual slide back towards thinking in stereotypical ways?
That could be really important for high-stakes, multi-step decisions, where you need the AI to consistently apply counter-stereotypical logic.
Precisely. Does the model hold on to the incompatible frame, or does the underlying easier association start to subtly reassert itself as the reasoning gets longer or more complex? It connects to reliability and consistency, especially in long context scenarios.
Fascinating stuff. And of course, the usual disclaimer applies.
Absolutely. These are just thought experiments, ideas to provoke discussion, building on the paper's findings, not definitive research plans yet.
Great food for thought. So wrapping this up, the big takeaway from Lee and Lai's work is pretty clear. Reasoning models show these internal, implicit bias-like processing differences. More computational effort for counter-stereotypical stuff.
Yeah, it really highlights that we need to look under the hood, beyond just the final output, to understand and tackle bias in AI.
It opens up new ways to measure and potentially mitigate these deeper biases as AI gets more sophisticated.
Definitely. And as these models get woven into more critical applications, understanding these nuances isn't just academic, it's crucial for fairness and safety.
Absolutely. We'll link the paper for anyone who wants to dive deeper. Thanks for joining us in this exploration.
My pleasure. It's important work to discuss.